things. So the idea of this form factor bootstrap is to be able to connect with the UV physics of the theory. So as you probably know, what our paradigm of how we think of QFT is as an RG flow starting from some CFT in the UV and ending somewhere in the IR in some other CFT. For the type of theories we're looking at here for gapped QFTs, we still expect some UV fixed point, and this would be just empty because all our particles are massive, so at some point we just don't see it if we go to low enough energies. So the idea of this form factor bootstrap is to be able to connect with this UV. And you can think of it as an extension of this S-matrix bootstrap setup we reviewed, in which we include some operator. Okay. So the idea is to extend S-matrix bootstrap setup to include some operator that I will call O. In principle, it can be whatever you want. And the idea is that now you can consider 3 types of different states. Before, we were looking at 2 particle states, in and out. Now we will have a 3rd type. So let's consider 3 states. The first one is this 2 particle in. Second one, 2 particle out. And the third one will be given by the Fourier transform of this operator acting on the vacuum. Sorry, I should say this, this extension was proposed in this paper by Karatev and Fenedonish in 2019. And so, okay, now we have 3 types of states, and we want to consider the inner product of these possible states. So we want this inner product, which will give some matrix I call B, Ij, with some delta functions. So this would be with momenta P prime, and this with P. And this P, because we have these delta functions in the end, will be just P1 plus P2, where you have the momentum of the incoming or outgoing particles. So let's construct this matrix. On the diagonal one, say psi1 with psi1, what should I get? 1, good. I'm already stripping out the delta functions. Then if I do psi2 with psi1, zero. It's the S matrix. Yeah, it's the S matrix. So here you get the conjugate. It's 0. No, it's not 0. It's not 0. Also 2 with 1. 2 to 2 is also 1. And then on this 3, 1 entry, you will get what is called a form factor. What's in here? You see you get the complex conjugate because you're looking at the reverse order for the inner product. Also here. And here. And in the 3, 3, you will get something called spectral density. This is why I didn't call rho the rho variable. And now unitarity will tell us that this matrix should be positive semi-definite. Okay, let me first just write the definition of the form factor. So for n particles, you would define it in this way. You can see with this iteration that you have here, if you translate this operator and act on the 2 particle or n particle state, in the end, you get these delta functions. So, okay, this is why you get the form factor. And the spectral density, let me call it p² here, will be the Fourier transform of the 2-point function of this operator. You can work out that indeed this is what you get when you do this inner product. So now let's look at this positive semi-definite condition, which applies again at physical values of the center of mass energy squared. And a way to evaluate what this condition is to just look at all the principal minors and set them, they should be positive or non-negative. So this is called Sylvester's criterion. So basically you eliminate rows and columns. So you see for the first one, you have just the S matrix, and the determinant gives you precisely our usual unitarity
Hi,
condition.
Lucía. Hi. Just to clarify, we're still in 2D, right?
Yeah, okay, this is the definition in general D, but we will be working in 2D, yes.
Thanks.
More questions?
Sorry, what's the difference between the form factors that we get within and out states? Like f of n, you define it with
You can
n
use
out?
CPT to relate
Okay.
them. This is why in the end you have just f and its conjugate.
Okay, thank you.
Good question. Okay, so we could have just written down this positive semi-definite condition for the amplitudes if we wanted to do it that way. Okay, so that we knew already. Then something new is if you take this other minor, then what you get is this condition for the spectral density in terms of the 2-particle form factor. Then you can also take just the diagonal elements. So, okay, this is already positive. We will have that rho, the spectral density should be positive. And the final one is when you take the determinant for the full matrix B. And this will give you some more complicated condition. where all three functions appear. Oh no, I won't have space. Okay. F, S. Okay. Something like this. So this will be our more general unitarity conditions. Okay. So as we saw in the numerics, but also more generally, if we are looking at some bootstrap problem, what probably will happen is that the optimization will saturate the constraints, or as much as it can. So what happens if we are saturating these constraints? So if at least most conditions are saturated, for the first one, we get unitarity saturation. I remind you that this S is actually the 2, 2, 2 S matrix element. Then if you input this on the last equation here, you get something called Watson's equation, which relates the two-particle form factor to the S matrix. And if anyone knows about interability, this is something they, yes?
The positive semi-definiteness. The two conditions, the positive semi-definiteness of the B matrix and the Sylvester's criterion, are they the same constraints? Yeah. Okay.
Yeah, so Sylvester's criterion is, I probably didn't explain it well. It's a way to evaluate what positive semi-definite means, which is all the principal minors should be positive.
Okay, thank you.
Okay, so as I was saying here, if you know about interability, this is something people use there, because the same way you can bootstrap the 2 to 2 S matrix, you can use this sort of equation to bootstrap the form factor. And if you look at the second condition, sorry, let me say first that this is natural. Why? Because F2 is, I said it's this, but I can insert here some complete bases. So I know this is related. Let's say this is, here I wrote out, let's say this is in. Then I will get the 2 to 2 for the first term here, amplitude, times the 4-factor complex conjugate, because I get it on the other side, plus the sum of n to 2 amplitude and the nth form factor. So I know there should be a relation like this. So when this condition is saturated, it's just sending this to 0, which makes sense. And from this condition here, you would say that the spectral density is given only by the two-particle form factor, which in general, what you would get using the same type of, just inserting a complete set of in or out states. In general, you should have this thing here. So it's just setting it to 0. what I want to say here is that if this is saturated, then this is actually just the two-particle contribution to the spectral density. So since we're only putting two-particle in and out states, what we get when we optimize things is usually just a two-particle contribution to things. So, okay, we don't want to put the spectral density to 0. Otherwise, yeah, we're not finding bounds on it. So here I just want to say that there is an iterable form factor Bootstrap that allows you to get F2 and rho 2 from S, and actually all Fn with some other extra things. So in some cases, you can construct this very explicitly when you have the theory, you know what theory you have. So what kind of operators can we use? In principle, you can do whatever you want. But something nice you can do is to use some conserved current, because that leads to some rules. So for instance, well, if O is a conserved current, then we have some rules that we can use to bound given parameters. So for instance, you could put the trace of the stress tensor into D, and you know this leads to the C theorem. So in other words, the conservation of the stress energy tensor implies this sum rule in terms of the spectral density of the stress tensor or the trace. So the sum rule looks like this. The difference between the UV and IR central charges is an integral of the spectral density over S squared. So, well, and as a reminder, C is what appears in the two-point function of the stress tensor. You have some C over 4, no, 2, yes. So it's one parameter that tells you basically which theory you're working with. It's a data of the CFT. So here, as I said, in the IR, we expect, well, this should be 0 because we are in a gapped phase. So you see that since we have the spectral density here in the game, we can get access to the central charge in the UV. So connect to whatever is happening in the fixed point there. So let's write it down, access to C UV. This is what the form factor Bootstrap does if you input this operator, but you can look at other operators. And something you can do, for instance, is to fix C UV to some value. If you want to study a particular theory, interested in or you could bound CUV in the space of allowed amplitudes or theories. So any question on this? I will show some plots so that you get an idea of which applications you can use. Can I take the screen down, please? Yeah, a question?
I mean, here, the summation of over n greater than 2, your form factor square is going to be 0. Can you?
In general, it's not 0. Here in this blackboard, I was just studying if we get some saturation from our optimization problem, as we often do. So we saw, for instance, for this monolith, we always get saturation of unitarity, just because we're only inputting information about 2 particles. So in general, if you just put information about 2 particles, what the numerics will do is to set these variables to be just a 2-particle contribution to it. So
and that was also the reason why this n, the summation over s going into 2 was 0?
Right.
Okay.
So this is if most conditions are saturated, the ones here on top. So if you have unitarity saturation, the last one, you see you drop the first term, and you get this Watson's equation. And here I'm explaining, indeed, it comes from setting these 2 to n or n to 2 processes to 0.
Okay, all right, yeah, thank you.
Yeah.
Okay, no, I was just wondering if you could motivate a little bit more the connection between the central charge, the difference in the central charges and the form factor, sorry, the spectral density. Like, for example, from the definition as the inner product between psi 3 and psi 3.
Well, the C theorem you can get just from thinking about the 2-point function of the stress tensor, and then you evaluate this condition that it's conserved. So yeah, you work out a bit, and in the end, you can write everything in terms of this 2-point function, which, okay, if you do some Fourier transform, etc., you can see this spectral density. Yeah, I didn't explain the derivation, but I can give you a reference if you want.
I see. Okay, so the spectral density that appears in the formula is when the operator is taken to be the trace of the stress tensor?
Right. Okay. So the last blackboard we don't see is everything for the stress tensor.
Okay, thank you.
Okay. Keynote. So yeah, I will just show some results you can get using this form factor bootstrap. And the first one is here. So in this paper here, the idea was to input some information about the UV, and in this way try to bound a particular theory, well, parameters for a particular theory. So they were studying Ising field theory, so the formations of critical Ising. So they set the central charge to 1/2 and study this Ising model for when you take the temperature out of its critical point below it, and also some magnetic field deformation, very small. And in this region, you have just one stable particle with some cubic coupling G, so that the amplitude will have a pole. Sorry, a pole, as we saw already, and the form factor will also have a pole like this, and with some coefficient F1, which is like the constant for the 1-particle form factor. So they were using, again, the operator is the trace of the stress tensor. And this plot here tells you which parameters are parameters for G, the cubic coupling, this F1, and then some X, which gives you the position of a 0 in this amplitude that is related to this magnetic field. What are the allowed values for these parameters? If you input this CUV equal 1/2, and they get this pyramid in which Ising field theory should live. And yeah, I should also mention that they figured out how to do the dual approach for this form factor, so this big matrix of 3 by 3. So that's one possible application. This is not supposed to be super understandable, it's just to get an idea of what things can be done. Another thing you can do is to locate a particular theory in your space of amplitudes, which, okay, it's the same as done here, but this is for a space you already saw, this leaf. So in this paper, what they did was to try to locate phi to the 4 in this leaf we studied. And what they did was to input some information about the form factor and the spectral density, again, for the stress tensor, that they compute with some other method, Hamiltonian truncation in this case. So you have some range of S where you know what this function should be. So you input that and try to locate where phi to the 4 is. And it's these crosses here for different values of lambda. So you see it's actually really close to this Sinch-Gordon model. But at some point, it gets inside the bounds as it should, because it's not an interval theory. It's just close to it for low lambda. Okay, they are using some other parametrization. It's not this S of 2, S of 3.9, but the amplitude at the crossing symmetric point and its derivative, but the physics, it's the same. And another thing you can do is for this ON monolith I explained, here you're doing the opposite. So we want to extract information about the UV in this space of amplitudes. So you can put a bound, say what is the minimum central charge you can have in this space of theories. So this is a temperature plot for a 2D section of the monolith, so the amplitudes at different points. And you can see is that, what you can see is that there are some, you can have low values of C in the middle. This would be the minimum you can have. And as you go towards the boundary, it grows. And actually, this bound diverges at big portions here of the boundary. So in particular, this periodic Yang-Baxter amplitude, this interval one I was mentioning, that has this infinite set of zeros with some periodicity, will have an infinite central charge. So that already gives you a hint that the UV is probably not what we would expect for a normal theory. We also did duals or rigorous bounds here. And something else we figured out is that actually this divergence on the central charge, since it comes from the sum rule of the spectral density that we cannot see, if you have this saturation, you can write rho in terms of F that you can bootstrap from S. So from the amplitude, just looking at the amplitude in physical kinematics, you can tell if the central charge will diverge or not. So this is what we call safe and dangerous points. Basically, how many times the amplitude crosses -1 with a given imaginary part. That will either make the form factor grow too much, and then the central charge will diverge. Or if you don't have any of these points, then you're in the safe region and the central charge is finite. Okay, that's for the monolith. And then a very cool thing you can do, I'm not sure if it's the first time it's used in higher dimensions, but okay, it's in 4 dimensions, and you can use this form factor bootstrap in pion scattering. So you might have heard Ifei's talk last week. And what they do there is to put some information about these form factors and spectral density for different operators you have in QCD. So in the UV, you can use perturbative QCD. This is this blue part here in the S-plane. Then you have this non-perturbative bootstrap in general. And for low energies, you also have some bounds from EFT. And including this UV information through these form factors, you can get something like the raw resonance that you wouldn't get otherwise. Or you can get, but you have a very big space of amplitudes. And doing this already gives you the raw resonance, which is nice. So you can see her talk. This is about the first part. So if you have questions about the plots. Okay, can we get the screen up again? Sorry.
So can you explain again how the fact that you have the form factors tells you something about the UV central charge where you couldn't get it without the form factors?
Yeah, so can you hear me? It's through this sum rule here, because the integral of one of the functions that you are adding here will be precisely the UV central charge. Okay, I got your point. Yes, you say, why can't I have just S and rho?
Yeah.
Because then you want them to talk to each other, right? So to have the full unitarity conditions on this restricted space of just two particle.
But rho is just something about your the spectral density of your theory, right?
Yes. But then you want to connect it somehow to the amplitudes, right? I mean, you could study rho by itself, it's fine, but then how would you connect it to S?
Okay, I see.
In other words, you really want to take all possible combinations of these three things and not just 3 and 3 and 2 and 1. More questions? Okay. So, yeah, let me pass to the last topic. So this is actually something that probably you heard about last week as well. Christian Copetti gave a talk. And this is something quite recent we found out. And basically, for this new type of symmetries that you can have, in particular these non-invertible ones, we'll see that it can lead to a modified crossing condition for the S matrix. So as you might have heard of, now there is a more modern version of what symmetries are. You can have some generalized symmetries. And the way to see them is as having some topological operators. So there is some operator that you can just move around in space-time. And basically, if you can move them in time, this will give you the usual charge conservation. So the paper that started this is in 2014. And this allows you to generalize the type of symmetries that you usually have. So now the familiar group-like symmetry will be a zero-form invertible symmetry. So to explain a little bit what I mean by this is that by zero form, I mean that they act on a local operator, these topological operators. that I can call U. Sorry, I forgot to say. So for instance, for continuous symmetries, you can construct these topological operators from the nether current. You exponentiate the nether current, and this defines some topological operator. In general, it's more tricky, but it's zero form because it acts on a zero-dimensional object, these local operators. And in general dimension, these topological operators for group symmetries will be d-1 dimensional. So of course, you have this group multiplication. So it tells you that having two different operators, you can fuse them to get a third one. And you should also have an inverse for each element. So basically, you can undo whatever you were doing before. So this is the group symmetry is called zero form because it acts on local operators, and invariable because there is an inverse. So what other things can you get? You can have Q-form symmetries that act on Q-dimensional act on Q-dimensional operators. And you can have also non-invariable symmetries for which you don't require to have this inverse. So I know this is quite abstract, but okay, just to get some key points. What I'm going at is to show that, at least in 2 dimensions, these non-invariable symmetries lead to new things on amplitudes. So what I will discuss here will be still in 2D, where I'm studying topological lines, so one-dimensional. But I don't require the inverse, so I have both invertible and non-invertible things. And I will denote these lines LA. So the mathematical framework to describe this is called fusion category, which I, of course, don't have time to review nor know enough about. But some ingredients that you need there to describe what the fusion category is will be some objects. For us, will be these topological lines. You will always have the identity there. You have some fusion rules. Where these coefficients here are called fusion coefficients and are positive integers. So you see, this is already something more general than the group structure, because you can have more than one thing on the right-hand side, and also you don't require this inverse. So you can have some element A, and you will never get one here. So it's okay, it's just something more general. There's also something called F symbols, which tell you how you can fuse things in different ways. Okay, we put some labels. CV, AB, CV, Y, U sum over Y. And this has all these labels. Sorry, I'm out of space. That also need to satisfy some other properties. For but the only one I will actually use is this quantum dimension, the A, that you define as the expectation value of a loop of this line acting on the vacuum. And you can also think of it as the maximum eigenvalue for these fusion coefficients when you see it as a matrix. So, okay, these are some of the ingredients you will see if you study something with fusion categories. Now, where do these things appear? They're actually not that uncommon. And for two-dimensional CFTs, they appear everywhere. Nothing happened. I shouldn't use this blackboard. Oh my God. So even in the Ising model, you already have a non-invariable symmetry. How am I doing with time? 15. Yes.
By the fact, I think it's, I mean, I'm still puzzled by the fact you were saying like there's no inverse element for this symmetry, but I'm still thinking of it as a group.
Yeah, the thing is, it's not a group.
Okay.
Or it's more general than a group. So you have the group containing it, but it's just a generalization of what symmetries can be. As long as you have a topological operator, you can get a symmetry.
Hi, Lucia.
Mm-hmm.
So the topological operators are 2D, and that's linking to an extended one-dimensional line, or is it linking?
Yeah.
Okay.
So we're starting lines in 2D that you can move around.
I see. And so in the previous discussion, O was a local operator, right?
Yeah.
Okay. And we're going to change that notion to?
Yeah, so wait a bit.
Thanks.
Okay.
Lucia? Just a quick question about, do you know what's the categorical nomenclature for these? What kind of objects are these? Like morphisms,
which ones?
functors, like what, like in category theory, like do they have a like a specific name for these objects, or is some sort of morphism or a functor?
Yeah, I'm not into the math lingua, so I wouldn't know. Yeah, there is something like that. I can give you a reference, but I don't remember. Okay, so there are many non-invariable symmetries, even in simple 2D CFTs. So, for example, the Ising model, you might remember that if you vary the temperature, there's some critical temperature where you have the CFT Ising, which is the first minimal model. And if you vary the temperature, you go to two different phases, one that is ordered, and another one which is disordered. And if you think of it of the spins going up and down, basically in this ordered phase, you have two possible vacua, either all spins up or down, and disordered just one. So here you can think of it as a C2 spontaneously symmetry breaking. And okay, you might remember there's also this Landau-Ginzburg prescription in which you can write this as a 5 to the 4 potential with different signs for this deformation. That gives you these two potentials. And no, I shouldn't have written this, because I wanted to use this. And maybe you've heard that there's actually a duality between the low and high temperature phases called Kramer's Vanier duality. But actually at the critical temperature, it's a symmetry of the theory. So for critical easing, the symmetries you have, we will write them in terms of these topological lines. It's, again, always the identity. Some eta line for the Z2 symmetry you have flipping the spins. And there is an extra symmetry, N, which is this, the one that implements this Kramer's Vanier duality. So the fusion rules for C2, since it's a group and eta is its own inverse, you have this. And for the Kramer's Vanier, you would get 1 plus eta. So you see, this is a non-invertible line, and you have two things here on the right-hand side. So the quantum dimensions for these lines are 1. And for the Kramer's Vanier, it's square root of 2. I'm writing this because in the amplitude, there will be some Ds around. So, okay, this is the simplest example. What about amplitudes? And the idea is that if you have some RG flow with some symmetry, I'll call it just C, this will give you, can give you very strong constraints on the IR. So for instance, it could tell you that you flow to a gapped phase with many vacua from 1 to n. So this is in the IR. But then we can consider amplitudes for particles that interpolate between these vacua. So these are called kinks. That will be in some multiplet, depending on the symmetry we have here. And what we will do in practice is to consider amplitudes, even just two amplitudes, for these kinks that interpolate between the vacua. These are the labels for the vacua. And these will define some S-matrix. So now, what does the existence of this symmetry imply for the amplitudes? If you want this flow to really have this symmetry, we should ask this amplitude to be symmetric. So we will have some word identities for S. So in pictures, we want to say, not putting a line here, it's the same as putting a line here. And this will give you some constraints on the amplitude. So you might have some sum of different elements here on the left-hand side and on the right-hand side that you should add to your set of constraints like unitarity, crossing, and analyticity. So the same way for the ON case, we knew what to write precisely because it's ON symmetric. We would like to do the same for these symmetries. So to give one example and to see an actual amplitude for these kinks. Why is it worse than before. Actually, I'll just write down here. So let's study probably the simplest flow that has one of these non-invariable symmetries. Let's do a deformation of three critical easing, which is the next minimal model. The first one was just critical easing. And do a deformation such that we end in a gapped phase with 3 of these vacua. So the picture is like this. Well, not like this. We start in M4. The operator you deform with is this 513, if you remember Descartes' notation for the primary fields of the CFT. And these vacua, let me label them by 0, minus, or plus. So the symmetry you have here is the same as in critical easing. Actually, because if you deform with the other sign of the operator here, you flow to critical easing. So the symmetries you have are, again, these 1, eta, and n lines. So what eta does for this vacua is to exchange minus and plus and 0 to itself. And what the n line does is to map 0 to a linear combination of the other two, minus to 0, and plus to 0. So it relates adjacent vacua. So the kink amplitudes you can have will look like this. Something like 0, minus, minus 0. You can also have plus. These kinks, I'm taking them to be the ones that interpolate between adjacent vacua. So you see already there is some relation to this n topological line. You can have things like minus, plus, plus, minus here. And also when you flip this around, so 0 on the other side. And these word identities that I mentioned earlier, I will write one of them. We'll give you some non-trivial constraint like this. So let's say I take the 0, 0, minus, minus, then, and I have minus 0, 0 here. So then I have the same here on the top. But now I have two options here in the middle. So whatever amplitude I have, it should satisfy this particular equation. So, okay, this is what we should have now that we know we have this these extra symmetries. But actually, I mean, these minimal models were known for a long time, and also in the interability community. Actually, I should say this flow is iterable, so you can bootstrap the S matrix. So people bootstrap the S matrix a long time ago without knowing about the existence of these non-invariable symmetries. And what you get using the Baxter equation, unitarity, etc. This was done first always homological in '89. You will get, let me call this hat, this amplitude in terms of this rapidity variable theta that was related to S through some cosh. There's some overall function that takes care of unitarity, some numbers, which is what you get from Jan Baxter. but actually will be the quantum dimensions of these lines. And then two terms, again with these d coefficients. A sinh of theta over n is 4 here, and sinh of I pi minus theta over 4. Now, crossing in this theta variable is sending theta to I pi minus theta. So t is I pi minus theta. So you see that crossing relates these two terms here. But you can plug this amplitude here and ask for this condition, and it just doesn't satisfy it. So this is using unitarity, analyticity, normal crossing, and Jan Baxter. So the normal crossing is A, B, C, D of theta is S, B, C, D, A of alpha minus theta, or S and T. And this is what you get. So you need this factor, for instance, to get this crossing. But it doesn't satisfy the word identities. So a very simple modification of this amplitude gives you an amplitude that obeys everything but crossing. So what we wrote down is basically S, just in interest of time, sorry. I'm going to say the homologic of 1, where you remove this overall factor, no, the C, the B to the I theta over 2 pi. So that you can check it. Really? Okay, it satisfies this word identity, but as you can see easily, because of this crossing relation, you pay this factor here when you do crossing. So it satisfies everything, but you need to modify crossing. In this way. The C, the B, D, I pi minus theta, B, C, D, A. So, okay, this is like the simplest example, but we actually have a way to derive this, basically from just unitarity and having these word identities for the symmetries. You can see that the amplitude for this kink state should obey this modified crossing. And I just wanted to show you a couple of plots. Can we get the screen down? Okay, I don't think there's anyone. But any questions while we get the screen down?
I think I'm a little bit confused by the physical picture. So in this case, these are things that interpret between
Backward,
solutions that interpret between. Thank you. So just to clarify the physical picture a little bit. So the kinks are solutions that interpolate between different vacua of the theory. And so what exactly is the S matrix element measuring?
You can still collide these kinks. So you can think of them at the classical level as just some solutions that really go from one vacuum to the other and take the scattering between those. So these are the amplitudes we were studying.
Okay, I think the thing that I'm confused by is the notation a little bit. So like
The notation is the labels are for the vacua. So the line interpolates between two different vacua, and this would be a kink.
I see. Okay, thank you.
Yeah. Sorry, it was very fast. Da, 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 da.
Lucia, what do you mean by these lines that you do with the word identities? Like, is there any conserved quantity associated to it? What is a word identity in terms of these symmetries?
Right. So they implement the symmetry transformation, and in this case, they would map different vacua between each other. So yeah, in this case, you can think of it as just acting on the set of vacua you have either in the in states or in the out states. That will give you the word identity.
Thank you.
Okay, so I told you one example of one amplitude we can write down, but actually you can do Bootstrap for non-iterable amplitudes if you just say, I have this symmetry given by some category, whatever. Okay, so instead of asking for Jan Baxter, as we did for this particular model, you would ask for these word identities. And to do that, you can just project into different fusion channels. And these projectors will be given by some F symbols, which are part of the data of the category. So for instance, in the category that is present in these flows from minimal models, these projectors are evaluated to these Kronecker deltas. Oh, I didn't write the Kronecker deltas. I'm sorry. There are some Kronecker deltas here. You can see that. This is why in the amplitudes, we would have like 0, 0, plus, plus. And then you ask for unitarity for these coefficients, A of chi. And this modified crossing will imply some condition, again, on this A of chi that were like our S of A for the ON monolith. So what is the space of possible amplitudes A of chi? We follow the same route as we did before. So for instance, for this AN category where you have n minus 1 vacua and n minus 1 topological lines, which fits into these deformations of minimal models, you can bootstrap the space of amplitudes without asking for iterability, and you will find a shape like this. I don't see my cursor, but okay. This blue line on the left. And at the cusp, you have an iterable point where you actually get this amplitude. So again, this model sits at a special point in the space of theories. There is some other type of category. Oh, it's here. Another category with 2 vacua and some other fusion rules. And here you can have a bound state. So you can do like a 3D plot for the different channel amplitudes at some given energy and this cubic coupling. And you would find some cone like this. And at some special points, again, you have some iterable theory, which is another deformation of the critical Ising model. Then at some other special point, you have a deformation of the Potts model. And the rest, we don't know what they are, but it's the first time we can see what kind of amplitudes you can get with non-invariable symmetries. So, okay, sorry, this was very fast. But I would just like to say that I showed you a very thin slice of what you can do with S-matrix Bootstrap. These are some active directions and people working on it. I am for sure not writing many others. And in view of time, I'll end here. Thank you.
All right. Thank you, Lucia. I suggest that we take 10 minutes break until 5 past. That we'll have our final lecture.